There's a few more things that I want to tell you about the Condorcet paradox. So just as a very quick reminder, the Condorcet paradox is just a voting situation in which there exists a Condorcet cycle. So the Condorcet cycle in this situation is that a majority of people prefer A over B, a majority of people prefer B over C, and finally, a majority of people prefer C over A. And this generates a cycle in the group preference ordering. So the question we're interested in is, what is the probability that such a cycle exists? So if we fix n voters and m candidates and allow them to choose their preferences however they want, we want to know how likely it is that we will see a particular profile generating a Condorcet cycle. So how prevalent is the Condorcet cycle phenomena? So the calculation of this probability is completely straightforward. What we need to look at is the number of preference profiles that actually generate a Condorcet cycle and divide that by the total number of preference profiles. So here a preference profile is simply a list for each voter, say there's n voters, 1 up to n, of those voters' preferences. So voter 1 might have preference R, voter 2 might have preference R prime, voter 3 might have preference R double prime, and so on. So we list all of the preferences in a list 1 up to n. That's the preference profile. So let's run through a simple calculation. Suppose that we have n voters and m alternatives. So the first question we need to ask is, we want to find the denominator of that fraction of the probability. What is the total number of preference profiles? So how many possible preference profiles are there when you have m candidates and n voters? So the answer is m factorial raised to the nth power. So as a reminder, just for the notation, m factorial is m times m minus 1 times m minus 2 times m minus 3 down to 1. That's what m factorial is. So you calculate m factorial and then you raise it to the power n. So how did we arrive at this number? So m factorial counts the number of ways that you can come up with a linear ordering over a set of m candidates. So the way we come to that number is we say, think about what a linear ordering is. A linear ordering, you have to say which candidate comes in first. So you write down a candidate that comes in first, then you write down a candidate that comes in second, then a candidate that comes in third, then fourth, down to the last candidate, which comes in nth place. Now, if we're considering any possible linear ordering, that means that any one of the m candidates could be listed at the first place position. So we have m choices for the first place position. But once you've fixed, or once you've settled on who comes in first, then that candidate can no longer come in second, third, and so on. So for the second position, there are only m minus 1 choices for the second position. So once you fix that candidate, that means there are m minus 2 choices for the third position, and so on. When you get to the last position, that means there's only one candidate left. So multiplying all of these choices together gives you m factorial. Now the reasoning for why we're raising this to the nth power is exactly the same. You write down all of the n possible voters, 1, 2, 3, up to n, and you note that each voter could possibly select any one of the m factorial possible linear orderings. So there are m factorial possible choices, or possible ways of assigning preferences to voter 1. There are m factorial possible ways of assigning preferences to voter 2, and so on. So every voter has m factorial possible choices. Again, multiplying all of those possible ways of assigning preferences to voters together gives us m factorial raised to the nth power. So to make things very concrete, suppose that we have 3 voters and 3 candidates. In that case, there are 3 factorial raised to the third power, so that's 6 to the third, so 216 different possible preference profiles. And so now our question is, how many of those generate an intransitive group preference? So first of all, you have to ask, how many possible intransitive group preferences are there? Well, if there are 3 candidates, then there are exactly 2 intransitive group preferences. First is A above B above C above A, and the second is C above B above A above C. Those are the only two possible intransitive group preferences. And then we have to ask, well, which preference profiles could possibly generate these intransitive group preferences? And here are the two preference profiles that could possibly generate these two Condorcet cycles, these two intransitive group preferences. So this means that there's a group 1, some group of voters, and they all hold the preference A over B over C. Group 2 holds B over C over A, and so on. So whether or not these actually generate an intransitive group preference, of course, depends on how many voters are assigned to each of the different groups. So for example, if all of the voters are assigned to this first group in this first preference profile, that means everybody ranks A above B above C. So of course, that will not generate this particular Condorcet cycle. But if these three inequalities are satisfied in either of these two preferences, so in either one of these two preference profiles, then you will generate the Condorcet cycle. So for example, if G1 plus G3 is greater than G2, well, that means that a majority of people in the first, a majority of people prefer A over B, so that'll give us a majority prefers A over B. In the second preference profile, that'll give us a majority of people prefer C over B. The second inequality gives us, so G1 plus G2 is greater than G3. This is going to give us that a majority of people prefer B over C in the first preference profile, and a majority of people prefer B over A in the second preference profile. And finally, if G2 plus G3 is greater than G1, this is going to tell us that a majority prefers C over A, and a majority in this profile prefers A over C. So as long as these inequalities are satisfied, then you will in fact generate one of these two Condorcet cycles. Now, if we only have 3 voters, the only way to satisfy these inequalities is to assign one voter to each one of the groups. So if there are 3 voters, then any one of those voters could be assigned to group 1. Any one of the remaining 2 voters could be assigned to group 2. And then finally, the remaining third voter has to be assigned to group 3. So that means there are 6 possible ways of assigning voters to groups in order to generate this Condorcet cycle, the first Condorcet cycle. For the second Condorcet cycle, the reasoning is exactly the same, so there will be 6 possible ways of assigning voters to groups to generate that cycle. Altogether, that gives us 12 possible preference profiles that lead us to an intransitive group preference ordering. Calculating the probability, it's just going to be 12 divided by 216, which is about 5.5%. So that's how likely it is that there will be a Condorcet cycle if there are 3 voters and 3 candidates. Now we can continue that calculation, and there's a famous table that was found or gathered by Riker in his well-known book Liberalism Against Populism. And this table lists all of the probabilities for a certain number of candidates and a certain number of voters. So one thing to note about these probabilities is that if we fix the number of candidates as the number of voters increases, then the probability that we'll find a Condorcet cycle also increases. But if there's a few number of candidates, then the probability, even as n tends to infinity, the probability will be bounded above by around 8.8%. But as the number of candidates increases, the probability that we will see a Condorcet cycle also increases. And in fact, it continues growing, and it approaches 1 as the number of candidates approaches infinity. And if both the number of voters increases and the number of candidates increases, then the probability that we will see a Condorcet cycle approaches certainty. So what that means is that we really should expect to see a Condorcet cycle all over the place. We should expect that if we have a large number of voters and even a relatively small number of candidates, then the probability is relatively high. So as n goes to infinity with 6 candidates is about 31%, 31.5%, that we will actually see a Condorcet cycle. Now, so this is an interesting theoretical result, but it does raise a question. Why don't we see more examples of Condorcet cycles when we hold elections? This data, at least on the face of it, suggests that we should see Condorcet cycles all over the place, especially when we have a relatively large number of voters. But in fact, there is relatively few non-controversial examples of a Condorcet cycle that we've seen in real-life elections. So what could possibly be going on? What could explain this discrepancy? Well, it's useful to examine two key assumptions that I was making when I did these calculations. The first assumption is that I did not put any restriction on which linear orderings the voters were allowed to adopt. This is called a no domain restriction assumption. So the voters, you can think of this as a freedom assumption for the voters. The voters were free to adopt any preferences that they want. The second assumption, which is a much more substantive assumption, is that not only were the voters free to choose any preference they want, but all of the linear orderings are equally likely to be submitted by a particular individual. What that means is if I pick an arbitrary voter, I pick a voter and I ask, well, how likely is it that that voter will choose any one of this set of linear orderings? That probability is going to be uniform across all of the voters. So for example, if there are 3 candidates, then there are 6 possible linear orderings. And if I pick an arbitrary voter, the assumption I was making is that the probability that the voter selected or adopted one of the 6 possible preferences is 1 over 6. And that is true for all of the voters in the population, no matter how big the population. So that means that, in particular, we are assuming that the voters' preferences are independent of each other. And this might strike you as a very unrealistic assumption, because after all, we have family and friends and we chat about our opinions, and it's natural to assume that our preferences, or at least the rankings we adopt in a voting situation, will be correlated with our friends and family. So the probability will not necessarily be uniform over the entire population about which of the possible preferences will be selected. So the assumption that the probability is uniform is called the impartial culture assumption. So that says that the voters' preferences are drawn from an impartial culture over the set of linear orderings. So that piece of jargon just means that if you pick an arbitrary voter, then the probability that that voter chooses a particular preference ordering is going to be uniform. It's going to be the same for all of the voters. It's going to be just the uniform probability measure over the set of all possible linear orderings. And you might question that assumption, in particular this impartial culture assumption. A number of researchers have done that, and what has been found is that as soon as you move away from that impartial culture assumption, then the probability of a Condorcet cycle actually goes down. So we don't have time to talk about how to prove this or how to go about understanding that. It's a bit beyond the scope of this course. I can refer you to this book, Behavioral Social Choice, by this group of authors. But the message, the take-home message, is that changing the distribution at all in any fashion whatsoever, whether or not you consider it a realistic change or not, any move away from the impartial culture assumption will automatically have the effect of reducing the probability of majority cycles in infinite samples. So what this means is that the analysis that we just went through is really a worst case analysis. So in the absolute worst case, then the probability will go up. And what you can find doing simulations and doing some analytic calculations is that as soon as you move away from this worst case scenario, then in fact the probability of seeing a Condorcet cycle actually goes down.